Lesson 8.1.1 Sampling Distribution of Differences in Two Proportions. Introduction. Pew Research Center conducted a nationwide survey to explore the media habits of Americans in 2014. This study considered the behavior of adults across 3 generations: the Millennial generation, born after 1980, Generation X, born 1965 to 1980, and the Baby Boomer generation, born 1946 to 1964. As part of the survey, the participants were asked about their use of 36 news sources, including social networking sites, major newspapers, radio programs, local TV, and major news networks. Among millennials, the most common source for news about politics was Facebook, 61%, followed by CNN, 44%, and the local TV, 37%. Similarly, about 51% of Generation X relied on Facebook for political news. The next 2 most popular sources for this generation were also local TV, 46%, and CNN, 45%. However, among baby boomers, the most common sources were quite different. Local TV was 60%, NBC was 47%, and Fox TV was 47%. Only 37% of this generation relied on Facebook for government and political news. In this lesson, we will compare the news and information habits of the millennial and baby boomer generations. In particular, we will compare the proportions of the adults who rely on Facebook for political news. Remember that P is the symbol for population proportion. Since we have 2 populations, let P sub M and P sub B denote the proportions of the millennial and baby boomer generations, respectively, who used Facebook as a source for political news in 2014. We will primarily use subtraction to compare the proportions PM and PB. So again, before we move on, the main difference between this section and previous sections is the fact that we have 2 proportions now, right? We want to know what proportion of millennials use Facebook for their news and what proportion of baby boomers use Facebook for their news. So because there's 2 proportions, that's why we have a PM, where the M is for millennial, and PB, where the B is for baby boomers. So let's keep going here. Suppose PB is equal to 0.37. Explain what this means. So this means... Oh, let me make sure that we're talking only about US. Does it say the US here? Yes, it talks about Americans in 2014. Okay, so this means the proportion of baby boomers who relied on Facebook primarily for political news is 0.37. Let me change this to US. So this means the proportion of US baby boomers who relied on Facebook primarily for political news is 0.37. Okay. Number 2, suppose that PM is equal to 0.61 and PB is equal to 0.37. What is PM minus PB, and what does this difference tell us? Well, let's go ahead and do the subtraction first. So PM minus PB is equal to 0.61 minus 0.37, which is equal to 0.24. So what does this difference tell us? Well, when you subtract two things and you get a number, that tells you how much bigger the first thing is than the second thing, right? So this tells us, that millennial, so the proportion of millennials, sorry, there's two N's in millennial, who use Facebook for political news is 0.24 more than for baby boomers. Okay, so that's what it means to look at the difference of two proportions. All population proportions are population parameters. Since PM and PB are population proportions, they are also population parameters. Since the difference, PM minus PB, is the difference in two population proportions, it is also a parameter. In previous lessons, we used sample proportions to estimate population proportions. In the following exercises, we will use a difference in sample proportions, PM hat minus PB hat, to estimate the difference in population proportions, PM minus PB. So just to talk about that a little bit, before we were using something like PM hat to approximate PM, or PB hat to approximate PB. But now what we're saying is if we want to approximate the difference, PM minus PB, we would just subtract PM hat minus PB hat. Let's look at this in practice. Suppose we take a sample of 65 millennials and 50 baby boomers. Suppose we find that 39 of the millennials and 20 of the baby boomers used Facebook as a source for political news. Find the value of PM hat, and what does this value mean? So what would PM hat be? Well, this is the proportion of millennials that use Facebook. So this is going to be, let's see, it says 39 of the millennials used Facebook, and that's 39 out of 65, right? So I'm going to do 39 out of 65. Let's go ahead and divide those in the calculator. So 39 divided by 65 is 0.6. Okay, what does this value mean? This means the sample proportion of millennials that use Facebook for political news is 0.6. Okay. Find the value of PB hat, and what does this value mean? So PB hat is equal to 20 out of 50, right? Because the problem says that 20 of the baby boomers out of the 50 used Facebook. So 20 out of 50 is 0.4. And what that means is, so this means the sample proportion of millennials that use Facebook for political news is 0.4. Okay. As percents, this would be 60% and 40%, right? Okay, so find the value of PM hat minus PB hat. What does this value mean? So PM hat minus PB hat is equal to 0.6 minus 0.4, which is 0.2. What does this mean? So this means that the sample proportion of millennials that use Facebook for political news is 0.2 larger than for baby boomers. Okay, so this is what it means when you get a difference. Next, suppose the value of PM hat minus PB hat were negative. What would this mean? So if you subtract two things and you get a negative number, all that means is that the second thing was larger than the first thing, right? That's the only way that you could get a negative from doing a subtraction, okay? So if PM hat minus PB hat were negative, this would mean that PB hat is larger than PM hat. So this would mean that the sample proportion of baby boomers would be larger than for millennials. Okay? Okay. Part E. Notice that the difference in sample proportions PM hat minus PB hat is not equal to the difference in population proportions PM minus PB from question 2. How can you explain this? So what are they saying here? So let's go back to question 2. They said suppose that PM was 0.61 and that PB was 0.37, and we subtracted them and we got 0.24 for the difference. However, over here, we subtracted them and we did not get 0.24, but we got 0.2. So why is that? Why did we get two different answers? Well, the simple reason for this is that these are samples and the other ones are for the entire populations. So both are approximations, right? So look at PM hat. In this case, PM hat was 0.6, but the real answer is 0.61, and that's because samples are always a little different, right? We know that there's variation. Also, the real PB is 0.37, but PB hat was 0.4. So the sample was a little higher than the real answer. The point of this is that because these are not exact, of course, if you subtract them, that's just going to approximate the real answer. So let's say it like this. PM hat is, okay, let me write it this way. And PB hat have sampling variability So PM hat does not equal PM, and PB hat does not equal PB. So, well, let me just say that this is true in general. So, PM hat minus PB hat does not equal PM minus PB in general. Now, I'm saying in general because it is possible that you could get a sample and luckily the difference will match exactly, right? If you happen to get the right sample, but I want to say in general, meaning you can't count on them being equal, okay? Okay, let's keep going here. Next steps. We have learned about sample proportions. Now we would like to understand the characteristics of the differences between sample proportions. In order to use a difference between sample proportions for statistical inference, we must understand sampling distributions of differences in sample proportions. We will now use a simulation to explore a distribution of the differences in sample proportions. Open the two-prop difference simulation at the link. Use the simulation to help you answer questions 4 through 8. So I'm going to cut to that right now so that we can continue. So I have the simulation pulled up here. Just as a note, it says Module 9 when you go to that website. So if you're running the simulation alongside me, don't worry about it. It's called two-prop difference, okay? So use this simulation to help you answer questions 4 through 8. In this spreadsheet, you can change the assumed population proportion and sample sizes. We will use the values from the previous exercise. Note that the symbols used in the spreadsheet are slightly different. The population proportion for the millennials is P1, and the population proportion for the baby boomers is P2. Set P1 equal to 0.61, N1 equal to 65. So let's go ahead and do that here. Notice that there's a P1 right here. I'm going to set this equal to 0.61. And then it says P2 is 0.37 and N2 is 50. Okay. Yes. Okay, I think this is set up correctly here. Okay, good. Now let's keep going here. It says the simulation creates 50 random samples of size 65 from the population of millennials and 60 random samples of size 50 from the population of baby boomers. The sample proportion for each simulated sample is determined. The sample proportions are used to create the histograms on the left. All possible differences, P1 hat minus P2 hat, are determined and graphed in the third one on the right. So guys, we have 3 histograms now. These first 2 should look familiar. So these are all the sample proportions for the millennials. What proportion of them like Facebook? And so this is us doing the experiment multiple times, just like before, okay? It says 50 random samples. So they're only doing 50, not 1,000 like it was before. Okay, so this is 50 samples of size 65 each sample. And then these are 50 samples of size 50 each sample. Okay? And these are the percentages. But we have a third one now. This is new. This is the third one, and these are the frequencies of P1 hat minus P2 hat. In other words, this is all possible differences. Okay? Okay. So, are the distributions for P1 hat and P2 hat approximately normal? Justify your answer. So, do these look normal to you? These look kind of bell curvy, right? Yes, because look at n1 times p1 and n1 times 1 minus p1. Aren't these both bigger than 10? Same here, right? The expected failures and expected successes are both more than 10, right? So let's come over here. Let me say, yes, all both distributions are approximately normal because they look relatively bell-shaped and the expected successes and failures are all above 10 for both distributions. Okay, so that's what I have for number 4. So let's go on to number 5. It says, look at the histogram that has the distribution of differences in sample proportions, p1 hat minus p2 hat. Does it appear that this distribution is approximately normal? Why or why not? Well, that looks really normal, doesn't it? So let's just say, yes, it appears approximately normal because it is bell-shaped. Okay. So this is good, right? Notice that these two are normal. That's what we knew from before, but now this one is normal too. Okay, number 6. What is the center of the distribution of the differences in sample proportions, p1 hat minus p2 hat? Well, we could try to eyeball where the middle is here, right? What would it be? It looks like it's about a little less than 0.28, right? That's what it looks like to me, right? Because the center looks like it's right below 0.28. Actually, right here, it says 0.246 is the mean, right? So it would be 0.246. So 0.246 is the mean of the differences in sample proportions. How does the center of the distribution relate to the centers of the individual sampling distributions? Well, it wants us to actually think about how the middle of this graph can relate to the middle of this graph and the middle of this graph. So I want you to think about it this way, right? If this guy is all possible differences of these two, it would make sense that maybe if you subtract this difference minus this difference, this center minus this center, it's going to give you this center, right? And that is actually true, because let's look at the center of the first guy. The center of the first guy, as we know, is 0.61, right? Remember, the mean is just p. So 0.61 minus 0.37, that's equal to 0.24. So it appears that the center of the differences in sample proportion is approximately the same as the difference in the centers of the individual sample proportions. So sampling distributions, sorry. Okay, so what I'm saying here in this answer is that if you look at the middle of this guy, which is 0.61, and you look at the middle of this guy, which is 0.37, and you subtract them, you get about the same thing as the middle of this guy, which is right around 0.24. What about the standard error? How does that compare? Well, this is a little harder to see here, but I want you to notice something. The standard error of this guy is 0.06. The standard error of this guy is also around 0.0. This one's like a little higher, right? 0.07. But the standard deviation for this guy is 0.09. What that means is that this guy is more spread out than these two guys are. So let's write that down here. The standard error of the differences in sample proportions is larger than the standard error of the original two sampling distributions. Okay, so let's I believe that's all we needed this for. So we're going to go back to this so I can handwrite and explain the rest. So coming back to our lesson here, you need to know the following things. A sampling distribution of differences in sample proportions, P1 hat minus P2 hat, is the distribution of all possible values of P1 hat minus P2 hat. The sampling distribution of differences in sample proportions is also known as the sampling distribution of P1 hat minus P2 hat. When two populations are independent, the mean of the sampling distribution of P1 hat minus P2 hat is equal to the difference in the means of the individual sampling distributions, which equals the difference in the population proportions P1 minus P2. Okay, so far this is all stuff that we saw in the last problem, right? So if you want to know the center of P1 hat minus P2 hat, it's just going to be the difference in the two original means, P1 minus P2. Differences of two statistics have greater variability than the variability contained within the individual statistics. Now here's something new. I want you guys to look carefully at this part. The formula for the standard error of the sampling distribution of P1 hat minus P2 hat is this giant square root formula, which looks bad, but really, if you look at it just as piece by piece, it's really similar to the old formula for the standard error. It's just that you have the two different population proportions underneath the square root. You've got on the left, you've got the P1 and the N1. Remember, P1 is the population proportion for the first distribution, and N1 is the sample size for the first distribution. And P2 is the population proportion for the second distribution, and N2 is the sample size for the second distribution. If the sampling distributions for both P1 hat and P2 hat follow a normal distribution, then the sampling distribution of P1 hat minus P2 hat also follows a normal distribution. So if N1 times P1, N1 times 1 minus P1, N2 times P2, and N2 times 1 minus P2 are all at least 10, then we can use the normal distribution to model the sampling distribution of P1 hat minus P2 hat. Okay, so just to, as an aside here as well, this part, this is just checking that the first guy is normal, and then these two are just checking that the second guy is normal, right? So all we need to do is make sure that each of them, the successes and failures in each sample is at least 10, and then we're good to go. Okay. Think about the example above using Facebook as a source for political news. Population 1 consists of millennials and population 2 consists of baby boomers. The proportion of the millennials who used Facebook is P1 is equal to 0.61, and the proportion of the baby boomers who used Facebook is P2 equals 0.37. The sample sizes we used were N1 equals 65 and N2 is equal to 52. So let's use those facts to answer these questions. So number 9, what is the mean of the sampling distribution of P1 hat minus P2 hat? So the mean is going to equal just P1 minus P2. And that's going to equal 0.61 minus 0.37, which if we do that in our calculator, it's 0.24. Next part. What is the standard error of the sampling distribution of P1 hat minus P2 hat? So we're going to get to practice using this square root formula, okay? So this is what we're going to use. So let's first put in the numbers, and then I'm going to show you what to do on the calculator. So what is this going to be? Well, P1 is 0.61 times 1 minus 0.61 divided by, what was the N1? It was 65, right? Plus, and then we have 0.37 times 1 minus 0.37 divided by, N2 was 50. So this is what we're going to put in our calculator, which looks difficult. It's really not that bad. So let's cut over to the calculator so you guys can see how to do this. So let's go ahead and try this out on the calculator. So we're going to put a giant square root symbol. So second square root, and then I'm going to put for the first fraction 0.61 times 1 minus 0.61 close parenthesis divided by 65 plus 0.37 times 1 minus 0.37 close parentheses divided by 50. All of that is under the square root. Now, if you don't have a calculator that elongates the square root like that, you need to put parentheses around the entire thing. But when I hit enter here, I get 0.091 as my answer for the standard error. So we got 0.091. Okay, that was what we got for the standard error. Make sure you practice doing that on your calculator so that you can see that you get the same answer as me. Is the normal distribution an appropriate model for the sampling distribution of P1 hat minus P2 hat? So for this, we do need to check to make sure that N1 times P1, N2 times P2, N1 times 1 minus P1, and N2, you know what, let me do this in a better order here. Let's deal with all the 1s first, and then we'll deal with all the 2s after that, okay? So we're going to do that, then we're going to do that, and then we're going to do that. So N1 times P1 is 65 times 0.61. N1 times 1 minus P1, 65 times 1 minus 0.61. N2 times P2 is 50 times 0.37. N2 times 1 minus P2 is 50 times 1 minus 0.37. Okay, so let me do each one of these in my calculator. 65 times 0.61 is 39.65, which is bigger than 10. 65 times 1 minus 0.61 is 25.35, which is also bigger than 10. 50 times 0.37 is 18.5, which is bigger than 10. 50 times 1 minus 0.37 is 31.5, which is also bigger than 10. So because all four of these are at least 10, right, that means that the first distribution is normal, the second one is normal, so this implies that normality criteria holds for P1 hat minus P2 hat, right? So we need to check, make sure that the difference criteria, the normality criteria holds for both. And if it holds for both, then that means it holds for the difference. Okay, so let's look at the next one. Number 12. On the graph below, use what you know about the mean and standard error of the sampling distribution of P1 hat minus P2 hat to label the tick marks on the x-axis below the normal curve. The distance between each tick mark is 1 standard error. So we're going to start by putting the mean, and remember the mean is 0.24. So I'm going to put that right here. And now what I'm going to do is, because the standard error is 0.091, I'm going to add 0.091 to this for each standard error. So if I do it the first time, I get 0.331. And if I add 0.091 again, I get 0.422. And if I add 0.091 a third time, I get 0.513. Now if I'm going backwards, 0.24 minus 0.091, I get 0.149. If I subtract 0.091 again, I get 0.058. And if I subtract 0.091 a third time, I end up with negative 0.033. Okay? So this is, remember, these are for differences. And yes, it is possible to get negative numbers when we're talking about differences, right? Because we're taking samples here. And it could be that the first sample that we're subtracting by the second sample is smaller, right? That gives us a negative. But in this case, that looks pretty unusual, right? So let's move on. It says, use the empirical rule to determine an interval that contains 95% of all differences in sample proportions. So what do we think here? I'm going to use a different color to picture this, right? Wouldn't everything between this and this give us 95% of the data, right? How do we know? Because remember, it's 2 standard deviations from the mean, right? That's the empirical rule. So it says determine the interval. So I will say 95% of the sample proportions are contained between 0.058 and 0.422. Okay, that's what this is saying. Okay, we're almost done here. Would it be unusual to find sample proportions P1 hat and P2 hat in which the proportion of millennials who used Facebook as a source for political news is smaller than the proportion of baby boomers who used Facebook? P1, so in other words, would it be unusual for P1 hat to be smaller than P2 hat? Why or why not? And what would the difference mean? So here's the trick, right? If P1 hat is smaller than P2 hat, then what would P1 hat minus P2 hat? Remember, we talked about this. If the first guy is smaller than the second guy, then that means if you subtract them in this order, this guy would be negative. Okay, so would it be unusual? Would a negative number be unusual? I would say yes, because look, 95% of all data sits between those two numbers. We don't start to get negatives until way to the left over here. And so, yes, it would be unusual, right? We usually expect to see things in that region that I posted there, okay? So yes, it would be unusual since it is more than 2 standard errors below the mean. Okay, let's keep going. Would it be unusual for the difference in proportions to be 0.40? Why or why not? And what would this difference mean? Well, let's look at 0.40. Where is it? Does it look unusual? So if I were to put that in my picture, let me use a third color, blue. 0.40 looks like it would be somewhere around here. So it's a little bit unusual, but not too unusual, right? Because it is within 2 standard deviations of the mean. Okay, so I'll say, since 0.40 is within 2 standard errors of the mean, it would not be unusual. And this would mean that, so what would this mean? This would mean that the sample proportion of millennials that use Facebook for news is 0.40 more, or let me say larger. That's a little more accurate here. Larger. Yikes. It's not letting me write this close to the top. Let me move it up a bit. Larger than for baby boomers. In other words, it would be on the high end, right? It's almost unusual, but it's not quite unusual. Now, what would be more unusual is getting a difference that's more than 0.422. That would start to get really unusual, right? Because that's when you get into this region over here. Okay. All right. That is it for this lesson. The code word for this lesson is boomer. That's right. The code word is boomer. Thank you very much for watching, everybody. Hope this video was helpful.